At today's office hours, James will be going over the agent lifecycle. So this is opportunity for hooks into code to do certain actions on startup, shutdown, different points of time during the agent, and that'll also be a good entry into just what underlies the base agent class and how you can build applications on top of it. Before we get started with that, any other questions or items folks want to bring up? No burning issues?
Jeremy, are we
Yep.
going to cover the simulation integration as well in this session?
Yeah, so if there's a time at the end of James's presentation, then Shweta will be covering integration between Volttron and a co-simulation framework called Helix, which is a fairly new and powerful simulation framework. All right. Well, if there's nothing else, then I will turn it over to James.
Hello. Jeremy, are you seeing the screen?
Yep, I can see your slides.
Okay, awesome. So I'm going to cover the agent framework kind of at a high level first. It might be a review for a lot of people on this call, but I'll cover it quickly. Then I'll talk about some of the agents available on the platform, and then go into the packaging module and the lifecycle. So in a general sense, agents are software agents are programs or modules that operate on behalf of the user to perform a variety of tasks. What those tasks are entirely specified by the user. In the context of Volttron, an agent is a software module that connects to the Volttron platform via VIP and performs Volttron tasks for the user. So common tasks are things like data collection, storage, retrieval. So that would be for those of you that have worked with the driver and historian frameworks. We have platform management agents, so like Volttron Central, Volttron Control. We have control agents. So that would be things like market services, transactive control agents, simulation integrations, like Shweta might talk about. We have a number of agents for sort of DevOps related tasks, like sending emails if a directory is full, sending emails if the topics being published to the platform are not being published or are out of a certain range, etc. But really, agents could be developed for any task the user might have. So on the platform, agents are packages installed and started by what is commonly referred to as AIP, but the full name is the Agent Instantiation and Packaging Module. And I bring this up here because the agent framework includes a number of features for actually implementing agents. So in Volttron, it includes an agent lifecycle, so managing, starting, stopping, and the loop while it runs. It includes a VIP connection with authentication, the ability to schedule tasks. It includes the config store feature, which I'm not going to talk about at length with, but it's an important feature for making the agent more responsive to the changing needs of the user. And then we also include the ability to integrate with the Volttron web framework. So if you wanted to serve web pages or operate the agent via something like a REST request, you would be able to do that. So we have a number of agents in the core services directory of the platform. Many of these things are historians or for working with historian data. So things like the MongoDB historian, SQL historians, and then aggregators for those tagging services, which will tag data for those historians. We have a master driver and actuator, and those are used to interact with devices to collect data, to set points, fetch points, you know, manage a keep alive, that sort of task. We have a number of weather agents. Currently we have 2 concrete implementations, but we have a base weather agent which you could extend even beyond the typical agent paradigm. And those will collect weather data from a number of endpoints. Currently we include a weather agent for weather.gov, and we also include one for dark sky. This might be a good time to bring up that, again, the dark sky agent is potentially going to fall out of favor for some users due to no longer providing API keys. And if anyone has any feedback about weather services they would like to see the Volttron core team implement a weather agent for, that is something we would really like feedback on. We also include a market service agent, which is sort of a baseline transactive control agent, as I understand it, which you buy and sell power through the agent, and then that agent interacts with other components on the platform. We have a few agents for passing data between platforms. So those are the data mover, external data, and forwarder. They perform different tasks depending upon sort of the connection paradigm. So if you're trying to, coordinate data across multiple platforms, or maybe push to a single sort of central platform, that kind of thing. We have Volttron Central, which is a management interface agent for managing multiple deployments or multiple platforms. And then we have a number of agents to provide specific interfaces for devices or protocols, and namely here I'm talking about the backnet proxy, which is an agent that is used to sort of fit the driver framework into the paradigm of the backnet network. So we also include historian agents. These are agents that are primarily designed to provide robust data collection capability. They listen to 4 different topics on the message bus by default: data logger, record, analysis, and devices. Each of those correspond to a type of data that are likely to, be desired to be collected by users, and that historian will collect that data, cache it for a short time before storing it in a database, and then that data can be queried through an interface that is available on the agent. And currently we have support for the databases listed at the bottom of this page: Crate, Mongo, SQL, etc. And there is a base historian for which, if you desired to make a database historian that isn't already included, you could extend the existing service to fulfill that sort of paradigm. Again, going to the operational agents, these are, kind of like I said earlier, for DevOps sort of tasks. So I'm not going to go into a lot of detail on each of these, but something like monitoring system resources, or determining if topics are above or below user-specified thresholds. Okay, so moving on to the actual agent framework. So this agent instantiation and packaging module I've been talking about serves the function of kind of preparing the agent module to be used with the platform, and then actually running the agent process. So agents in Volttron are installed as wheels in the Volttron home directory. They each are given their own installation directory that follows the paradigm of using the unique identifier of the agent and then its name. And then in there will also be the agent's keys, an agent data directory for the agent to populate with data at runtime, and a number of other things relevant to the agent operation. And then when you start the agent, the AIP module will run it as a separate process from Volttron. So, you have Volttron running as the user that you've started the process with, and this will spawn another agent with the same user by default, but in a separate process. And then if you're using the secure agent feature, that will cause agents to instead be spawned with agent or user, Unix users, which correspond to only that agent. The purpose of which is to isolate that agent's ability to modify data. So if you had installed agent, some agent, it wouldn't be able to, modify other agents running on the platform. There are some other functions associated with AIP. It's responsible for setting up the agent identity and tag. It will, beyond just managing the agent process, it stops and starts the agent. It supports the Volttron control agent utilities to do so. So when you're running Volttron control commands to control agents, it actually runs through AIP. And it does a little bit of the background work for setting up the secure agent environment. So setting up the Unix user group for agent users, and then creating those users and setting up their directory permissions. A little bit briefly, so we provide an agent configuration store. This is a mechanism by which the user can dynamically change the configuration of agents as the agent runs. The config store will essentially trigger a callback when a configuration changes, which will allow the agent to handle that change ad hoc. When the agent configuration is stored, it's given a unique name based on how you've stored it, and those are added to that agent's config store in Volttron Homes /configuration store. So for instance, you have a master driver running on the platform. By default, that agent's identity is platform.driver. There will be a platform.driver.store in the configuration store directory in Volttron Home. And then as you add configs, those will be stored in that store. Supports JSON and CSV, and I actually think it also supports YAML, if I remember correctly. And those will be added to the store and then sort of handled by the agent when that update is triggered. There's a few other things you can do with configurations. You can have configurations that reference other configurations. You can have configurations be shared by references. So you have two driver configurations that both share the same registry, for example. And there's some protection built into that, so you don't have like some sort of weird circular reference that infinitely triggers updates or something. Okay, so moving on to the agent lifecycle, we have I'm going to say base agent class. It's no longer called base agent, but base agent is found in the init.py in the VIP agent directory of platform, and that code is responsible for dealing with instantiating subsystems and the core class specific to the message bus that is being run. So then each message bus implements a core that manages the communication with the platform. So that's where the agent is actually connecting to the message bus and manages the authentication for the agent when it's connecting. and that sort of thing. And then
James, you mean that each agent creates a code that maintains a connection with the message bus, right?
right. I'm sorry if I misspoke there. And then once those things have been created, there's a run. The core has a run function which then actually performs the agent startup, main loop, and then finish. So during that process, the agent will use signaling to trigger a few functions in the user specified agent to perform tasks that the user would want to have happen when the agent is stopping and starting. So there are 4 of those signals. Those are on setup, on start, on stop, and on finish. Each of them have a specific purpose that I'll go into in just a moment. But also in this main run function, the agent core is responsible for dealing with scheduled tasks. So if you want to have functions run as greenlets, core supports the ability to schedule a callback either at specific times using scheduling like cron, or setting it a number of seconds later, but also through what we call periodics, which, as the name would imply, just periodically call the function. So if you want a function to be called maybe every 5 minutes. And then the actual loop, which occurs sort of naturally between on start and on stop, is where the agent sort of allowing the user to specify the functionality, and it sort of waits for the agent to close, and then deals with closing after the loop is completed. So going back to those signaling methods, we have the first one that is triggered is the on setup method. So the way you would typically sort of specify these in your code is you would have some function that you want to be called when this signal is sent. Typically, you would actually name it sort of corresponding to whatever that signal would be. So if you're doing an on setup, you would define an on setup function in your agent implementation, and then you would specify a decorator that has a core.receiver on setup. So this will be what is sort of dealt with by that signal. And then, so this is the first one that's done. This is generally called to do things for setting up the state of the agent. So if for some reason you had set up that you wanted to do, after the instantiation of the agent class, but before the actual main loop started, as far as managing state, this is a likely candidate for a place you would do that. From what I could tell, just going through the core repository, this is maybe one of the functions that's used a little less than the others. And then, so immediately following that setup is when those scheduled tasks are being set up. And I'll kind of circle back around to scheduled tasks in a little bit. And then following scheduled tasks being set up, it triggers another signal which deals with this on start decorator. So again, it works the same way, where you define a function and supply a decorator, and then it performs this on start function. This one I think is used a little bit more than on setup, and typically, or historically for me, what I've used this for is initiating like threads where I want something to happen, periodically. So if, like I was talking about periodics earlier, for example, if you were going to pull weather agent data, you might set up a periodic in your on start to go and pull that data from a remote API. I mean, there's a number of other things you could do. This is where you might set up subscriptions to message bus topics. So if you're a control agent interested in a number of of topics on the bus to determine if your algorithm should do an adjustment. This is where you might set up a subscription for that as well. Okay, moving on, we have, this is sort of the main loop summary. So essentially, the main loop will just kind of continue to let the user specify the function and manage those greenlets until one of two unhandled exceptions are thrown, which is a greenlet exit and keyboard interrupt. The first of which is kind of done by the platform generally. And then so we also have you know, VIP connections and subsystems which are being handled asynchronously during this loop as well. So then after the main loop has finished, we've, you know, for example, if the user has supplied a keyboard interrupt, immediately what has happened is that all of the scheduled tasks are killed. So we kill off all of those greenlets, and then we send the on-stop signal. So just like the previous two, this is one of those decorator methods. Most typically, this is used for stopping some kind of cyclical tasks and setting up an end state. So for example, one thing you might do in on-stop is if you made a database connection, you might close your database connection here. And then after the on-stop is done, it calls an on-finish. I think this is another one where this is probably one that's used a bit less often. The one that I saw most recently was actually, I've seen database connections being closed here as well. You might also do this for final logging or, you know, cleaning up files that hadn't already been dealt with, that sort of thing. And then, so going into periodics for a moment. So there's a couple of ways to handle periodics, and essentially the two main ways you would set those up in your agent code would be either a function specified by a decorator or a function that is triggered by a callback that you specify in the agent code. And I will bring up a little bit of agent code here for you. One moment, sorry. Okay, so we can kind of see some of those things I was talking about before as well. So like, you know, it's often the case that, you know, you could do something like run on setup via that signaling. But typically with state, it's also the case that you can handle that in init and configuration, which is what's being done here. But if we scroll down here, so this is where, okay, we've triggered an on start via the signal in that run function, and when we start, we're saying, okay, we want to periodically try to actuate a point on a device. So we've specified a 30-second interval for calling that function. So this is one of the two ways to do periodics in a general sense. So you just would call the agent's core and then specify that you want to run a periodic. The other option would be to do a core periodic decorator with the appropriate arguments, so a period or in a function to call. And then if you wanted to do a scheduled task, so you wanted to schedule a specific time, again, you can do core schedule and then specify a schedule and a callback, or you can do a decorator on a function with a schedule. And for schedules, I've seen, again, cron jobs and so a certain time period from from the start of the schedule call. And then going back to our presentation here, the sort of last thing that I have to cover is that there are a couple of caveats that we wanted to cover. So for one, if you have a scheduled or periodic task that is likely to be long running, what can happen is if that task doesn't complete by the next schedule or next periodic call, you get this sort of accumulation of these asynchronous tasks. So in general, it's sort of recommended to run these long-running tasks as greenlets rather than actually running them through the core periodic. And then the other one is that if you're performing long-running tasks or computation on setup and on startup, you're essentially delaying the main thread of execution for the agent. So if these can be done asynchronously, it's a good idea to spawn greenlets in these functions that handle those tasks, and then allow the main agent loop to actually begin executing. Okay, that's really it for this. Are there any questions?
The other thing is that if you have don't do any time-consuming computation task within the callback of the subscription handler. This will delay the agent from getting the next set of messages.
Either that or make sure you call gevent sleep within it.
Yeah.
One of those two.
Okay. Shweta, are you ready?
Yeah, sure. Can you guys see my screen?
Yep.
Okay. So the topic that I'm going to discuss today is so this task has been going on for few months now. This is related to simplifying integration with different types of simulation platforms. So we have different type of simulation platforms here at PNNL, developed locally in PNNL and also elsewhere. So if you want Volttron to integrate with all these different types of simulation platforms, earlier we had individual agents.
Dan, I'm getting some background noise from you. I'm going to go ahead and mute you. Sorry about that. All right. Sorry, Shweta.
Yeah. So earlier we would have special agents that directly connected or integrated with the simulation platform. So it came a point where we had these different agents that were integrating to the simulation platforms directly. So we decided to have a simulation integration framework, follow the same design pattern that we have for historian framework and other frameworks. It is not always easy to have different simulation platforms follow the same framework that we have developed, but we have tried to adhere or fit it into the framework model as best as we can. So different platform co-simulation platforms out there. There's Phoenix, there's Helix, which has been recently developed here at PNNL in collaboration with other national laboratories like NREL and LN, Lawrence Livermore National Laboratory. So that so the first task that I took up was coming up with this base simulation integration class and develop concrete integration class that allows you to connect with Helix. Then there's Grid Apps D and also Energy Plus. Energy Plus agent has been around for quite some time. We just tried to clean it up a little bit and fit it into the simulation integration framework that we have developed. Though all these simulation frameworks have or simulation platforms have their own use cases, and it has been developed for different type of scenarios. There is some commonality in the way they all run, and we are trying to address that or use that to come up with this framework. So all the simulation platforms typically have a start method, have a stop method. All of them have an internal clock which is used to synchronize different components that are connected to the simulation. Then they have some register methods that allow you to subscribe to the topics or messages to receive from the simulation platform. And similarly, there are some APIs or methods with which you can publish some data into the simulation. So taking these common features into consideration, the basic steps that we came up to for integrating with Volttron is start a simulation, subscribe to outputs from simulation. Once you have received the simulation, if you want to republish it on the platform on Volttron, then publish outputs received from simulation to Volttron. Then if an agent wants to interact with the simulation platform, then subscribe to topics from Volttron and feed those messages into the simulation. This is related to data exchange. Then there are a set of APIs that are related to time synchronization. So if you want to advance the time step, so as I mentioned, there is a timing mechanism within the simulation. I'll touch upon that a little bit later. There are other features that may or may not be provided by the platform simulation platform. Features such as ability to pause the simulation or ability to resume the simulation. If those features are provided, then the concrete simulation integration class that I developed will have a wrapper around those APIs to pause and resume the simulation. So in this framework, we have example agents that show you how to integrate with Helix, how to integrate with Grid Apps D, and how to integrate with Energy Plus. These simple example agents allow you to show you how you can develop your own agents and allow and enable your agents to communicate with the simulation and come up with complex power systems or building to grid scenarios for your experiments. So the features, as I mentioned, ability to start the simulation, and then ability to register for inputs from simulation. So typically we have a config file where you can configure some of the features or some of the configurations for connecting to the simulation itself, and then a set of configuration parameters that allow you to configure or register to inputs from from the simulation, such as if you have a simulation that is simulating electrical vehicle and you're interested in getting the charge point value of the EV, then there will be a topic or a data point that you can register to receive in order to receive that data. Similarly, you can register for inputs, register for outputs that are generated by the simulation. I'm sorry, register for the outputs. I'm getting confused with outputs and inputs. Inputs are those that are being sent to the simulation, and output is that is being received from the simulation. So if you have some data to be sent to the simulation, you can configure it in the input section. And if you have data that needs to be received from simulations, for example, outdoor air temperature from Energy Plus and so on, you can receive it by configuring those topics in the config file. Briefly, I had touched upon time management in the simulation world. In the simulation environment, typically there needs to be a global timekeeper or somebody who's keeping track of time so that all the participants or entities that are connected to the simulation are in sync with respect to time. Typically, we have a global timekeeper that is keeping track of time. In Helix, Helix broker has a timekeeper that is keeping track of time. The tracking of time can be periodic. There is a periodic timekeeping, which periodically you can advance in time. Say if you have configured periodically to advance 1 second of simulation time, then the global timekeeper will take care of advancing the time. Otherwise, if you have a case where the other way to do it is the participants decide when to advance in time. So in that, that is typically a time request, time grant kind of scenario, where each of the participants would request for a certain time when it is done with its work and get blocked until it is granted that time. The global timekeeper that would then look at all these time requests and look at which is the lowest among these time requests and then advance in time with the low based on the lowest value. So generally the simulation advances in time in this manner. So if the Volttron agent that is interacting with the simulation will have to send a time request message to the simulation to advance in time. And this is all taken care of inside the concrete simulation integration class and is hidden by the user specific agent or the example agent that I'm going to show you now. Then, like I said, have concrete methods that allows you to pause the simulation or resume the simulation. This is basically a wrapper around the APIs that are provided by that specific simulation platform. Then the ability to stop the simulation when required. You unregister all the inputs and outputs that have been registered with the simulation and disconnect from the simulation platform, and also stop the agent. These are the APIs that are provided in the base simulation integration class. The start simulation, it connects to the simulation platform, register with the platform as a participant. Register inputs will take in the configuration file that you have and then register all the configuration parameters with the simulation platform. And if you have a callback method specified, then based on the outputs that is received from the simulation when it is ready is transferred to the callback method of the agent. Similarly, at some point of time when the agent is ready to publish some message to the simulation, then it can typically use publish to simulation to send the message to the simulation. make time request allows you to request to the simulation to advance in time. Some simulation might have the ability to provide time steps. Typically, it is configured, and it will, if you configure it, it will automatically take that and advance in that time step. Then there's pause simulation, resume simulation, and stop simulation. So I was talking about configuration. So typically, this is an example of a Helix configuration file. So you have, before I talk about the configuration file, I'll talk about what Helix actually is for people who do not know about Helix. So Helix is a co-simulation platform that is open source, general purpose, modular, highly scalable co-simulation framework that runs on Linux, Windows, Mac, and so on. The predecessor of this was Phoenix. Phoenix, though, was developed a few years ago, around the same time that Volttron was developed. Since then, they have moved over to Helix, which is highly scalable and can run on high performance computing platforms. So you can run very, very high, large scale simulation experiments using this co-simulation framework. So the participants in this co-simulation framework platform are called federates, and you can have you can come up with different complex power system scenarios where you have a distribution network, you have a transmission network, you have building models and things like that, all connected and interacting with each other seamlessly. So if you have a distribution network developed or simulated using GridLabD, then that becomes a federate or a participant. And then if you have a building or a transmission network developed by some other tool, then that also becomes a federate. And you can connect all of these data, all of these tools together, and allow them to exchange data during runtime and stay synchronized in time so that you can develop complex power system or building to grid scenarios and run experiments on them. Volttron can also be integrated with Helix. When you integrate Volttron with Helix, or have an Volttron agent that is connected to Helix, then that Volttron agent also becomes a federate and is able to exchange data and be synchronized in time with the rest of the federates in the simulation, in the co-simulation, Helix co-simulation world. So I'm going to just paste this in the chat window for people to is the chat. Just looking at time. There's 15 minutes more. Okay. So that's a little bit of a background on Helix. Now coming back to the integration of Helix, of Volttron with Helix. So as I mentioned, you need to have a config file. The format of the config file is how it looks here. So we have a properties section, and this format is similar to will be similar for Helix as well as Energy Plus. We couldn't adhere to this format in GridAppST because GridAppST is more complex. We tried to, because it's doing the same thing that we are trying to do. We're having, it has these different federates all trying to, connect to each other and um, um, interact with each other seamlessly. So it has its own configuration format, and we couldn't adapt or have a good cohesive way of merging that format with the format that we have developed. So like as I mentioned, it's not always one-to-one mapping, so it's difficult to map, but we have tried to have the same config format for at least Helix and Energy Plus integration. So the properties section will contain the name of the federate. In case of Helix, it's the federate. In case of Energy Plus, it will be something else. Then you have the log level, and this is typical to the Helix, the type of core that you have, or the type of message bus that Helix uses. Right here it is 0MQ. It has support for TCP, UDP, MPI, and so on. Then you have time delta. This is the time in which the simulation advances. It is currently set to 1 second. Then the total simulation time length is 360 seconds. And this is the section where you configure all the outputs that you want to receive from the simulation. So the first is the simulation, Helix simulation topic. Then if you want to republish that message that you received from Helix onto the Volttron message bus, then you can configure that using Volttron topic. Then the type of data, the data type that is being received, and so on. All of this is then registered with Helix as part of register to simulation step. Now this configuration is related to that the stuff that needs to be published to Helix. If you have a publication topic like pub1, then the type of data type, the data type, and then the unit. And if you're receiving that from another agent in Volttron, then you can configure that here. So when you receive that message from another agent on the Volttron message bus, immediately that is wrapped into a Helix message and sent to the Helix simulation. Then Helix has this special property where instead of a publish subscribe mechanism, if you want to directly send messages to a federate. In my case, I am going to show an example where there is Volttron agent running, which is acting as one federate, and there's an example another Python federate that is acting as the second federate. So you have two federates. One is sending to another directly. So if you want to send directly to that endpoint, then you can do that by specifying your endpoint, which is federate 1 EV6 and the destination endpoint. So if you send a message from endpoint EV6 to endpoint EV6 on federate 2, so this is the name of the destination federate and the endpoint of in that federate. So you can send from this source to this destination, and type of message is a general message. It's like a string, and then it's a global it can be a global endpoint or a local endpoint. I'm not an expert in Helix, but I just know enough to make this integration possible. So this is for direct communication between the two endpoints. And this is for publishing to the Helix using pub/sub mechanism. So with this information, let me move over to an example that I have here that showcases how you have to set up Helix. For this to run, first thing that you have to do is install Helix on your system. The installation steps for Linux-based installation is over here in this link. Then, in order to run this example agent, what you'll have to do is, in an activated environment of Volttron, you'll have to upgrade the pip installation, because if you want the Python support for Helix, you will need to have pip version, a higher version, 20 or I think 20 something. So you need to upgrade that and then install Python support for Helix. For the example agent to run, pip install Helix will do that. Then this is about the configuration itself. Then Helix has this concept of a broker and a federate. So like in Volttron, there is a central entity, which is the Volttron platform or the router in 0MQ message bus case, which is responsible for routing messages from one entity to another. Similarly, Helix broker is responsible for routing messages from one federate to another. And it needs to know how many federates are connected to it. And it's also responsible for the global timekeeping. So you need to start the broker with, so I have the setup ready. In the top right window, I'm going to start the broker by saying that there are two federates that are going to be connected to it. Then what you need to do is install the example Helix agent that we have developed by pointing to the Helix federate config file that I just showed to you. I've already installed it and I have it set up here, which is on the top left window. I'm sorry, yeah, top left window. So I have that running. Let me stop that so that I can restart it later. And then the third thing is the start another Python federate for it to communicate with each other. So I have that here in the same agent folder. So that's here in the middle window. And this is the log to show you that the data is indeed being exchanged. So I'm going to start that, start the example agent, which will be the federate one. So this says that it read the config file and made all the registration. So the concrete simulation integration class that we have developed will do the registration on behalf of the agent. So it has registered all the endpoints, it has registered all the subscription keys that we have configured, and it has also registered all the publication or input keys that we have configured. Then it enters into an execution mode where it is sitting and waiting for the Helix broker to go ahead, you can start simulation. And the broker will not start the simulation until it has received the connection from all the federates that have been mentioned here. So when you start the second federate here, which is just an example, it will move from execution mode to this actual simulation mode. So here you can see that data is being exchanged between the two continuously. So there is data that is being sent from federate 2 to federate 1 using the typical publish subscribe mechanism that Helix and Volttron understand. And also data is being exchanged to single endpoints mentioned here. So if I stop this, if you see here, data is being sent from FedRed 2 EV6 point to FedRed 1 EV1, because a similar config file is also provided in the Python FedRed that we have. So there's another complementary config file that is in the other FedRed that tells you, okay, which is my endpoint and which is the corresponding destination endpoint. So the corresponding destination endpoint configured in the other FedRed is FedRed 1 EV1. So the data related to FedRed 2 EV6 is actually received in FedRed 1 EV1. Similarly, I'm sending some data from one endpoint from FedRed 1 endpoint to FedRed 2 endpoint, which is received on the other side. That's about endpoints. And then the agent is also publishing some data on this topic, input topic here, pub1 topic, which is being received on the other side, on the other FedRed here. FedRed 1, pub2, and pub1, both are being received here. So apart from that, every time it receives the messages, it receives the output from the simulation, each of the FedReds are advancing in time. So that's why you see the time interval 333 mentioned here, 32332 mentioned here, and so on. So both are advancing in time, 1 second at a time. And that's how the simulation, co-simulation works. So you have Volttron as a FedRed, you have a Python example as another FedRed, you can have GridLabD connected as another FedRed. Probably you can have GridAppsD or MatPower simulation as another FedRed, and they all can work together in a cohesive manner. And that's all I had for today. Hopefully I can continue with this to show you how GridAppsD is being integrated with Volttron, and then how Energy Plus is integrated with Volttron. So this way you can expand the universe of Volttron to work with other co-simulation platforms and come up with very complex building to grid or power system scenarios.
All right, thank you. Any questions on that or on the agent topic? If not at this time, if you have anything that you want to ask, feel free to ask the mailing list or email us directly at volttron@pnnl.gov. We'd be happy to follow up on these topics or anything else. And if you have a topic that you'd like to present, that would also be great. I think at the next office hours, we'll be hearing from Andrew Rogers about some UI library work that ACE IoT has been doing. In addition, James Larson will go over configuring BACnet devices. That's a topic that we've had a couple of queries about. So if you have anything else that you'd like to hear, please let us know. And since we're at noon, if there's no questions or comments, we'll call this a meeting. Thanks, everybody.